So it's a great pleasure to have Djordje Radicevic from Brandeis, who normally would be visiting us to give this talk. And sadly, it has to be through Zoom. But nevertheless, it's great to have Djordje talking again. And Djordje, for those of you who don't know, put out this epic series of papers recently, and I cannot imagine even writing that much, never mind computing that much to write. But he will give us a talk on an introduction to the Lattice-Continuum correspondence, and I think I'd advertise it as the infrared structure of QFTs, right? So
it's the same thing, yeah. So the title changed a little bit, but it's the same thing. So thanks, Jeff, for inviting me, and thanks everyone for coming. So today I'm going to talk about these three papers that I've written and posted recently. They total to around 300 pages, so I will naturally only talk about a small order 1% of the entire story, but I will try to give you a gentle enough introduction to the entire subject so that you can get motivated or annoyed by what I say, and then inspired to think more about it and possibly even read the needed sections of the papers. I will focus on the more big picture stuff, like on the more abstract, slightly more abstract stuff. But along the way, I will give some examples, and I will definitely point to where in the papers you can find these things written in more detail. So as usual, feel free to ask questions, interrupt, criticize, whatever you feel like. And let's start. So the name of the game here is essentially trying to understand what QFTs are and how to think about them, and these big picture questions. So there are really two polar opposite approaches to what a QFT is. In practice, what people do is usually they work with one or another or some hybrid of the two, but just having the idea of these two extremes is useful. And I'll use that as my starting point for this talk. And then I will explain precisely what I mean, what I'm going to do in my talk in the next slide. So the approaches are as follows. One thing that's the sort of more popular approach, and the one that is almost universally taught to all students, and that is more intuitive, is what you might call a continuum quantum field theory approach. So at its most abstract, this is an idea that QFT is some mathematical object which takes a manifold, takes some nice geometric space, and spits out some partition function or correlation function, or some numbers which you can then use to calculate various probabilities of physical processes. And the important thing here is that everything is sort of nice and conforming to our everyday intuition. So you have these nice smooth manifolds, and the only things you compute are various interdependent functions in these manifolds. So for instance, a function that just takes a manifold of some sort to a number, you may call a partition function, or a function that takes a manifold with certain marked points or marked lines on it, possibly labeled by, let's say, representations of various symmetry groups. So if such an object taken to some complex number, you can call a correlation function. There's no need for me to go into details. Like these are the kinds of things that are sort of built into the foundation of the bootstrap way of thinking about quantum field theory. But it's also, this kind of approach is also what you do when you start learning QFT from, let's say, Peskin and Schroeder. You just compute these kinds of objects perturbatively, but you are effectively computing just a series of some interdependent correlation functions, which you then use to calculate probabilities of processes. So so that's the very standard continuum way of thinking about what a QFT is. And then there is a complete opposite way of thinking about it, which I will call lattice QFT. Now, various versions of lattice QFTs or lattice theories have been known for decades, and in particular, Wilson is famous for formulating general lattice gauge theories and making the lattice approach useful for gauge theories and for QCD and things like that. But here, I'm going to sort of be more Wilsonian than Wilson in that regard. So when I talk about a lattice QFT, I will mean something very specific. I will mean a quantum system. So something that obeys standard rules of quantum mechanics that you learn even before you learn QFT. And it has a finite dimensional Hilbert space. The Hilbert space can possibly be exponentially large in some number, like it can be 10 to the 10 to the 23 or something, but it still is finite for foundational purposes. It can be a product of many smaller Hilbert spaces, for instance. And all of physics is contained in this one Hermitian matrix, the Hamiltonian. So if you can diagonalize the Hamiltonian, you know everything about the dynamics of the system, and you know everything is perfectly natural and intuitive. Like everything is contained in everything is given by simple linear algebra. In this approach to QFT. And you can put it on a computer, you can simulate it, and so on. You can define it easily, and etc. Now, both of these approaches are familiar to all the practitioners. One more than others, one more than another, perhaps. But the question I want to ask is a question that one doesn't often ask, which is what is the connection between them? And not just at some vague level, but what is a precise connection? What's the best we can do in terms of elucidating the connection between these two ways of thinking about QFT? Are they actually the same? Or if not, what is their overlap, and how should we think about QFT? Or so this is the question. This is the point of my entire epic trilogy, which will be followed if everything goes according to plan with another trilogy. So the familiar story. So the question is, what is the precise relation between these two ways of thinking about QFT? And of course, if you are familiar with more advanced topics in QFT, you know that there is a deep set of ideas going back to Wilson and Kadanoff and other people in the 60s and 70s, Polyakov, for instance, of course, saying that there is a connection between these things, that if you have some lattice system and you somehow bring it near a conformally invariant point in parameter space, then it starts behaving like a continuum theory. It forgets the details about the lattice, it forgets the details of the regularization, and only depends on these like nice smooth global properties. That's all very nice, and it's absolutely amazing. I don't want to diss this approach, but it's not precise. It's not fully precise because it really works well for few point correlation functions, and doesn't really say much about how it fails once you start looking at extreme values of couplings or correlation functions of many operators and things like that. So the standard approach of thinking about how continuum theories are connected to lattice ones works really well when you are only interested in certain correlation functions, but is not good if you're interested in fancier objects like entire operator algebras, let's say, or other interesting non-perturbative phenomena. Nowadays, interesting non-perturbative phenomena go under the headings, ramp and plateau, for instance, in certain circles. So you're probably familiar with that. So these are the kinds of things that universality a la Wilson does not address well. So the question is, can we do better? And how can we do better? So there are hints that correspondence between lattices and lattice and continuum QFTs is both impossible and unavoidable. So let me very quickly highlight both. These are just hints and signs, and I do not want to think of any of them as silver bullets or anything. Like all of these have loopholes, but they're just arguments that you may see, and I want to highlight them. So, for instance, you can often hear statements that a certain continuum QFT cannot be latticized for various reasons. For instance, various chiral theories, especially with or theories with fermions more generally, often run into various no-go theorems if you try to naively put them on the lattice together with a bunch of other properties that you may want. This goes back to this theorem, to this pair of theorems by Nielsen and Ninomiya. So that's one familiar and old argument that you might not be able to latticize everything. Then a more modern statement is that continuum theories have unfactorizable Hilbert spaces or unfactorizable operator algebras, or type 3 operator algebras, whereas lattice theories have factorizable ones. So they can't possibly be the same kind of object. This can often be phrased in other ways. Sometimes you say, oh, continuum theories have an infinite amount of entanglement at short distances, and therefore all bets are off. Or you may say, oh, lattice theories cannot have fancy properties of the continuum theory, like OPE structure, because you can't get two operators in arbitrarily close to each other. You can only get them either a lattice spacing away or on the same side. You can't do anything in between. So that sounds like another obstacle. And then there's the general fact of life, which is that we don't really have any kind of good model for various interesting continuum phenomena and various interesting continuum theories that can be that lives on the lattice. So for instance, if you try to lattice gravity or various interacting supersymmetric theories, we run into problems. We just don't really know how to do it in any kind of tractable way. So maybe these things are not latticizable. Maybe everything has to live in the continuum. On the other hand, there are certain arguments that say that you kind of have. Oh yeah, please go.
Just on the last point that you made regarding latticizing gravity, I mean, what would you consider sufficient to have a good latticization of gravity? So what's wrong with the Reggie tessellation, for example?
Well, okay, so
or are we talking about quantum?
Yeah, I'm thinking of quantum gravity. So Reggie gravity is fine as a classical theory, but I definitely do not know of beyond things like two-dimensional gravity. I do not know of good Hamiltonian formulations of quantum gravity. So okay. I would certainly say that we do not have a good one. Okay. There are dynamical triangulations and things. So I'm not saying that there aren't any models or work done in this direction, but I am sure that there is no universally accepted latticization of some theory, which in some classical limit gives Einstein gravity in 4D, let's say.
All right.
Yeah. So and then a sign there, one sign that is a bit vague but still interesting to talk about, that given a continuum theory, it really has to somehow come from something that's well regularized, like a lattice theory, is the existence of various entropy bounds. So for instance, we know that you cannot have, especially if you have gravity present, we know that you cannot have an infinite amount of information stuck in a finite volume of space. So that's one way to say this. Or another way to say it is that if you have some continuum theory but wait some exponentially long time, then you will start probing the UV structure of it. So you kind of have access or have arguments saying that there are ways for a continuum theory to rediscover its UV origins. And then there's, of course, the fact that even though there exists a plethora of theories that we cannot laticize, we don't know how to analytically, tractably laticize, like, let's say, transimence theories. We certainly know that there are experiments with an explicitly finite number of degrees of freedom, which give rise to effective transimence descriptions, like, quantum polyfacts. So that's an argument saying that, the problem is really in us and not in lattices necessarily. So something has to give. Like, you can't have both impossible and unavoidable correspondences. So my point of view is that, of course, that the correspondence is effectively going to be unavoidable. I'm not going to give general arguments for this, but instead I will show in much more detail than was ever available before how such a correspondence works. Meaning, how do you start from a lattice theory and derive something that is a continuum theory through some well-defined systematic truncation of the lattice theory. So basically, how to extract a continuum theory out of a lattice one. That's the goal of the entire series of papers, and this turns out to work pretty nicely. And not only does it give a completely new way of thinking about QFTs, it also helps elucidate a lot of phenomena and a lot of disparate ideas about various models in various dimensions that have been floating around. So let me intuitively describe what I mean by this correspondence, by this systematic procedure. So I call it smoothing. So this is something you do on a lattice theory to give you something that is also a lattice theory, but that up to a specified precision behaves precisely like what you expect a continuum theory to behave like. So all fields very smoothly. There is a notion of OPEs. There is a notion of non-factorization of algebras, etc., etc. So all of those things can be seen to arise from a particularly natural truncation of starting lattice theory. In some ways, this is like RG because it's a systematic reduction, but it's not the same. And you will see in the next slides precisely what I mean by this new procedure. So the main benefit is, to me, foundational, because it really gives you a way to precisely define various QFTs. And as far as I can tell, it should work for, it doesn't have to stop at, simple QFTs. You can do interesting things and think about interactions and so on. And in particular, so basically it thinks of continuum QFTs as some effective theories that arise from a lattice. And one thing that I particularly like about this approach is that it is extremely explicit about the hierarchy of cutoffs that must exist in your continuum theory in order for it to remain continuum-like. So what I mean by this is that often people say, quite sloppily, that the continuum limit of a lattice theory is obtained by just taking the lattice spacing, which is effectively just the inverse of the number of lattice sites, just taking that number taking the spacing to be small, and possibly tuning the couplings. What I'm going to say is that this is not sufficient to define a continuum theory starting from a lattice one. You need to have other cutoffs in place. And I will be very explicit about this. And so basically your continuum theory, you should view it as an EFT which has several scales, several ultraviolet scales. And as you go to higher energies and cross each of them, different phenomena will happen. And the continuumness of the theory will be violated in different ways. So this I have not explored at all from the effective field theory side, but people who like effective field theories should like at least what I'm saying. I'm basically giving them extra toys to play with by saying these things. And then the main shortcoming of this entire story, and I'll be very explicit and honest about it, is that it doesn't actually help you solve QFTs. So if I give you some complicated interacting lattice theory, like something that I hope to be lattice QCD or the standard model or something, My approach will not help you solve it beyond maybe providing some extra self-consistency tools to use to check any ansatz you might have. So in that sense, it's kind of unlike Wilsonian RG because it won't actually help you write down a super nice effective field theory later on. So just a warning that from some points of view, this can actually look like, I'm not giving you something super powerful, but foundationally, it's really useful and new. So because certain provocateurs have asked me this, I should say that this will not necessarily prove the existence of a mass gap or something like that in Yang-Mills theory, but it will certainly recast the problem in ways that are new, and that are, at least to me, much more tractable than the current formulation by Vinton and Jaffe, let's say, in the official statement of the problem. So that's the intuitive idea of what I'm doing. And then let me sell the idea a little bit more by telling you about the kinds of outputs that these papers have, that the thinking about this has. So of course, the main thing that I already emphasized is that this gives you a formal definition of continuum QFT. And this is a definition which does not require you to spend 2 years learning operator theory and functional analysis. It's a theory that it's a definition which requires you to know what the matrix is. So it's so much nicer and more user friendly in many ways. But it has applications to actual specific physical systems too. So, for instance, there exists a set of models, especially 1+1D, which is of great interest. You can call them clock models. They have ZK symmetry, and K can be taken to be very large. In that case, you may call them rotor models or quantum rotor models or XY models or something. They're super important in condensed matter, and fundamentally they're important also in string theory. For instance, it is known that these lattice models have a very interesting line of fixed points, the BKT regime, that exists as long as a specific coupling is smaller than some critical value. Now, it turns out that this gives you a very interesting handle on, it resolves this line of fixed points into a cascade of symmetry breakings of this global ZK symmetry. So basically, this line of fixed points is really a collection of different phases, if you will, or at least regimes, in which a different subgroup of this ZK is broken, and so you can end up viewing the gapless degrees of freedom in the CFT as Nambu-Goldstone bosons of a subgroup of this ZK, and you can make this precise by using these procedures that I said. And I'll just make it precise, but you can actually calculate things like operator product expansions of vertex operators in this regime straight from the lattice, just using the lattice data without ever assuming that there is such a thing as conformal symmetry or using anything fancy. You can literally just set up a calculation which only involves doing a simple sum, and you will get the scaling dimensions of vertex operators and things like that. So that's, and it also highlights limitations of what is colloquially called the Mermin-Wagner theorem, because it turns out that it's sufficiently low couplings, you can indeed break symmetries, even continuum symmetries. The K goes to infinity versions of these in 1+1 dimensions. So this sort of puts continuum and discrete symmetries on the same footing, and tells you what you precisely mean by continuum symmetry. And on a related note, this also allows you to generalize Noether's theorem to discrete symmetries, because now I will probably not talk about this in the paper, but in the talk, but I can use this approach to actually formulate Noether's theorem for arbitrary symmetries, not just continuum ones, and so I can compute, like, let's say, the Noether current for charge conjugation symmetry. It turns out it's just a total derivative, and so it's the nether charge is going to be 0. So it's not as useful as other nether currents, but nevertheless, it's nice to know that there is no fundamental difference between continuum and discrete, continuous and discrete symmetries in this formulation of QFTs. And then there's other stuff. One thing that I will talk about in this talk, after giving this formal definition, is the way you actually get various counter terms and contact terms in your continuum theories. So, for instance, there is I can give you a lattice-based derivation of the induced Chern-Simons term that you get when you integrate out massive fermions. So, that's one way of thinking about how Chern-Simons arises from a completely finite, well-defined lattice setting. So that's nice. And that in this example, I can explain in 5 minutes in the 0+1 dimensional case. So how one-dimensional Chern-Simons arises from quantum mechanics of massive fermions is something I can beautifully explain in a few minutes. So that's what I will do. And then there are other things that this gives you a handle on. So it gives you a handle on new ways to define various supersymmetric theories on lattices. It gives you ways to start from lattice dualities, which are exact, and derive the emergent infrared dualities in continuum theories, like the ones I have listed here. So in addition, it not only allows you to derive them, but it also gives you bounds. It tells you which operators map under these infrared dualities and which do not. At what point does the infrared duality stop working? So it gives you quantitative ways to think about talk about all of these things. And then there's some more things which are completely new. Like, for instance, thinking about gauging various lattice symmetries gives rise to various new anomalies which have not been reported before. That's also an interesting subject which I will totally not have time to talk about. If any of this interests you, then ask me after the talk or read the paper, or just think of it on your own. But I'm going to focus on these two topics that I have circled here. But yeah, I can take a few quick questions right now if you have any. And if not, I'll launch into actual details, and as opposed to just advertising specious results. Okay. So let me give you a formal definition of what this smoothing is. So it's a crank that you will be able then to apply to your favorite lattice theory, in case you actually have a favorite lattice theory. So the context in which I will define it is as follows. I will work completely in the canonical formalism, which is slightly unfamiliar to many people, but ultimately it's just Hamiltonian formalism. It is, you have learned it in school. So I'm going to be on a single time slice. So time is just a continuous parameter, and in fact, for my intents and purposes, it doesn't even matter if time is Minkowski, if time is Euclidean or not. So everything is defined on a single time slice, and everything is discrete. So as I said, my lattice theories are completely regularized. So both position space is a lattice, and the target space of my theory is going to be a lattice too. So everything is perfectly regularized. Those are the starting points. And then everything that I say can be rephrased in the language of path integrals, but I will not do it in this. That just adds extra degrees of complication at this point. I don't need it right now. I will talk about it a bit later. And here is the schematic way of how this works. So you start off, you define this procedure algebraically. So you start off with some lattice theory, which has an operator algebra A, which is essentially just some collection of D by D matrices, where D is the dimension of the Hilbert space. As I said, a possibly large, but still finite number. And then there is and then I will propose a specific procedure that chooses a subalgebra of this original algebra. I will call it AS. And every operator contained in AS is going to behave like a continuum operator, meaning that it will vary smoothly in space, and there'll be a natural notion of an OPE that you can define for it, etc. Now, I'm going to stress that all the operators that live in AS are still defined on a lattice. So in that sense, they have not, I haven't embedded the lattice in some like underlying continuum space or anything. Basically, I'm just choosing operators from a lattice theory which behave like continuum operators. So the direction of the way I'm thinking about this may look upside down to you, but it's consistent and leads to nice definitions of everything. And the other thing I mentioned is that the proximity to the continuum limit, the sort of the continuumness of the operators contained in this AS is not governed by the lattice spacing or by the number of lattice sites. It's actually governed by another parameter, which will enter the definition of smoothing, and that I will make explicit later. So it is wrong to say that, as I said, taking the lattice spacing to 0 is enough to give you the continuum limit. There is another parameter that needs to enter, at least another parameter, and depending on the complexity of your theory, you might have more. So yes. And finally, I will stress that not every lattice theory has a continuum limit. Not every lattice theory has a smoothing procedure that can be applied to it. There are two criteria that I will explain on the next slide that tell you whether a starting lattice theory can be smoothed into something that's continuum-like. And these two criteria I call the existence of a pre-continuum basis and a corresponding existence of a natural sense of distance or topology on the momentum space. So I will explain what these things are, but right now I'm just stressing that not every lattice theory will have a continuum limit. In fact, only a select set of lattice theories will have continuum descriptions, will be smoothable, which is of course not surprising. If you pick a random Hamiltonian, it of course will not be correspond to a continuum QFT. Good. So that's the game plan. So let me first describe what these conditions are. So the pre-continuum basis is something that is actually relatively familiar. It is a generalization of a Fock basis. So basically, a pre-continuum basis is formed by a complete set of operators that all commute. So basically, and not just commute with each other, but commute with the Hamiltonian, as you can see here. So what I mean by this is that your theory has to have a large number of conserved charges. I will call them NK. And these charges I expect to be in this form. So they will behave like particle number operators. They will each of them will act non-trivially only on some subspace of dimension JK, and it will be assumed, and they will be assumed to be normalized such that their spectrum is this. And that's why I call them particle number operators. And different commuting operators are going to be labeled by a label K that lives in some set P that I will call momentum space. The labels K I will call momenta. But at this point, and this is super important to stress, at this point, the label K is just some abstract label. It has no obvious connection with whatever starting lattice position space I had. Depending on the theory, it may be just a Fourier transform of the original lattice, but in many theories, this will not be the case. So right now, think of K as just an abstract label for these commuting operators. And you can also define ladder operators, CK and CK dagger, which just take for a given k, take one of its eigenstates to another. Just change the eigenvalue of nk by 1 or -1. So in the usual way. And these ladder operators, by the completeness assumption, these ladder operators generate the entire algebra A. So their products and linear combinations are precisely the entire algebra A. That's what I mean by a pre-continuum basis. And so I should make two remarks. So this differs from the usual Fock basis by the fact that I'm not assuming any kind of commutation relation that holds between different CKs. It can be anything at this point. And I'm also not assuming that that there is any notion of identical particles. So things at different Ks can have different different levels, different possible occupation numbers, etc. So it's really not the same thing as a Fock basis, it's a generalization. And the second thing I should say is that the existence of the pre-continuum basis, the fact that I will need that to define a continuum theory, implies that a very sneaky thing. It implies that continuum theories are defined as essentially through the integrability of the underlying lattice theory. So normally we say, oh, a continuum theory arises if the underlying lattice theory is in some point in parameter space where there is some emergent conformal symmetry or scaling variance at least. I am saying that instead of thinking about scaling variance, I'm proposing to think about integrability as the guiding principle to when there exists a continuum limit. And this is nice because it also allows me to define massive continuum theories in the same process. Like I do not have to think about conformal perturbation theory or irrelevant operators or anything like that. So the procedure I will give you will work for both extremely massive, including topological theories, and massless theories. So yeah, good. So deep down inside every continuum theory is an integrable or ultimately free theory. That's one of the starting points here. That is sort of forced upon me, as you will see. And then the second criterion. So not only do you have to have a pre-continuum basis, but the Hamiltonian has to play nice with it. So if you have a pre-continuum basis, the Hamiltonian can always be written as a polynomial in the particle number operators, like so. But it's important that the Hamiltonian also endows the momentum space with some structure. So, and the natural way to do this is to say that the Hamiltonian is dominated by these coefficients next to the linear terms in the particle number operators. These coefficients I call dispersions. And if the Hamiltonian is sort of dominated by them, if all the other coefficients are small, then I can say that nearby momenta, I can define that momenta are nearby if their dispersions are close to each other, as you can see here. So basically I can use energies as proxies for differences between momenta. And then I can say, and that allows me to define a low energy subspace by simply referring to a momentum subspace, like so. And that in turn allows me to, without talking about specific Hamiltonians or further talking about energies, that allows me to pick a subset of the momentum space, call it PS, that is governed by, that is essentially a ball that it contains of momenta that are in some small region of size Ks in momentum space. Ks is some integer, so this Ks is just the number of different momenta in this region, and I can focus on this momentum space, on this subset of the momentum space, which is effectively the low energy space, and projecting to something that's related to this PS is going to be the key step in deriving the continuum limit, and the ratio of the total momentum space to the subspace, to the low momentum space, is going to be this extra parameter that I keep harping about. That's the ratio that's going to control everything. So I did not specify, but you see here that like the pre-continuum basis implicitly has a large number of momenta So that corresponds to saying that the lattice is large in some sense. So it's the inverse of this, of the size of the momentum space, which tells you what's the lattice spacing. But it's really this ratio instead, which tells you what is the proximity to continuum limit. So both PS and P are large, but the ratio is small, and that is going to be the parameter that controls my continuumness, as you will see. So these are the two things that I need. So I need there to be a pre-continuum basis, and I need the Hamiltonian to somehow be dominated by dispersions. Or this is not the unique way for a Hamiltonian to induce a notion of locality on the momentum space, but it's by far the easiest one to explain. Good. So these are the preliminaries. So assuming that there is this nice structure present in the Hamiltonian, and now how do I smooth? So it's a projection. It's a simple projection to a subset of operators, to a subalgebra, in fact, that is generated by the following operators. So you pick a low momentum subspace or a low energy subspace, ES. And then the smooth subalgebra AS is generated by the following. So you take all the operators at low momenta. So you take all possible products of all possible ladder operators at low momenta. They are all allowed to stay in the algebra. But above KS, so outside of the low momentum subspace, you only keep the momenta. Sorry, you only keep the particle number operators, and you project away all the ladder operators, the individual ladder operators which can change your particle numbers. So that forces, that means that NKs have to form the center of your smooth subalgebra. So the only pure states you're allowed to talk about in this context, the only pure density matrices that belong to AS are those of states which have a fixed occupation, which have fixed occupation numbers, which are eigenstates of all the high momentum NKs. And one way of thinking about this is to say that there is a fixed amount of high energy, of high momentum entanglement in all the states that you have. So that paves the way to that statement that I said earlier, that continuum theories have an infinite amount of entanglement at short distances. So what I mean, the lattice version of it is to say that these states have a fixed amount of entanglement that does not change with time, and it can be exponentially large. It can grow with the size of the lattice or something, but nevertheless it is fixed. And that sort of tells you why it's sort of important to even have this notion of, integrability, or the notion of there being constant particle number operators, NK. If you didn't have that, then your smoothed theory would always have transfers of entanglement from high momenta to low momenta. So that would be terrible and sad. And you want your continuum theory to be something that possibly has a lot of underlying entanglement, but at short distances, but still does not randomly leak out quantum information into the high momentum modes. And then, so what does this projection allow you to do? So basically, if you look at the Fourier transforms of these guys, of the CKs, these Fourier transforms are precisely what you call quantum fields. And their projections into the smooth subalgebra are precisely what you call continuum quantum fields. So these are these C of K objects that I wrote down here. What I mean by X here is the following. So once you have identified the momentum space, and once you have used the Hamiltonian to specify some lattice structure on it, some notion of distance and so on the momentum space, then you can imagine taking a Fourier dual of it so Fourier transforming all of your CKs into CXs. And this Fourier dual I denote by M star. So the reason I denote it like that is because it's not the same as the original lattice M, whatever it might have been. So so you use the Hamiltonian to determine what your PKs are, what your P's are, what your momentum space is. And importantly, it doesn't even have to have the same dimension as the original P. And in fact, every time we find an example of some, lattice theory which has a different dimensional P, we get super excited. So an example is string theory, where you really start from some CFT, like a minimal model or some bosonic theory that lives on a 1+1 dimensional manifold, but then somehow you actually realize that it's really describing a continuum theory that lives in a 25+1 dimensional space, in the bosonic case, let's say. Or ADS CFT is of course another way. So you have some complicated lattice theory, which we call for better or worse n = 4 super Young-Mills, but then we realize that it's really given by somehow weak interactions and free particles in one dimension higher. So I'm stressing that this P does not have to have the same dimension as the original lattice, but you can always think of Fourier transforming the P, whatever it is, and you will get some smooth, and you will get some quantum fields C of X after projecting the original lattice operators or their Fourier transforms. And the really nice thing about this projection is that the way I have phrased it is implies that all of these smooth fields will obey the following kinds of smoothness constraints, meaning that as you move by one lattice spacing on the lattice M star, you will only change these operators by a small amount, by this ratio that I stressed on the previous slide. And this essentially comes from the properties of Fourier transforms. Basically, it says that because you do not have high momenta anymore in your Fourier expansion of C of X, you've projected those away, then that forces C of X to be a smooth function on the lattice scale. So,
Djordje, can I ask a question?
Of course, yes.
Do you care what the geometry of your lattice is? I mean, are you necessarily assuming that it's a flat lattice or?
Good. So I am being, of course, coy about those details. The explicit examples I will give, or the explicit examples I have in the paper, are all on flat lattices, but in principle it can be curved, and I mean then instead of Fourier transforms in the standard way, you'll be thinking essentially about using generalized versions of them, right? Using, think of spherical harmonics or some versions of that. So these Ks can indeed be vectors, and the Fourier transform may not be a simple, sum over e to the I kx, but it may be a sum of some more complicated functions. Basically, what I'm thinking about is that this transformation, the originals, you can define Cx as something like as a sum over Ck, and then you have some function which you can call Gkx, and this is the eigenfunction of the discrete Laplacian on your lattice P, whatever it is, and then you can and this goes over all P, and then you project, then you smooth, and you get this new operator Cx, where you have some smoothed version of this guy. So this is what I have in mind in general, but for all the examples I will give you, everything is flat. And working out the details for the curved ones is an open question, but I do not think it's a fundamental obstruction to this entire study.
But for example, if I take some curved lattice and I open it up by inserting some defects with some opening angle, for example, then I could do, then your formalism goes through on your formalism for the flat space, the flat lattices goes through, except with some finite set of defects or something like that.
That is, yeah, that's also true. So you can do it piecewise, but another thing that I will stress is that then these guys here will just be no longer, just e to the ikx, but they will become something else. So you can just substitute those functions in, which, and these functions will be something that's sort of piecewise defined on your lattice. So they change over as you cross the defect.
Right,
so,
okay, cool.
So yeah, so it's doable, but it's annoying, and for illustrating the purposes, it's not important. But of course, for practical purposes, one should find a good way of thinking about this. But I do not think it's going to be a huge issue. It should be a fertile ground for papers, but yes, it's just me tooting my own horn here. So yeah, right. And then let me in particular stress how naturally operator product expansions come out of this story. They come out as follows. So this smoothing is actually remarkable because it does not commute with operator products. And the reason is simple. The reason is as follows. So you can have two operators, OX and O tilde X, that are built somehow out of these CKs and CK daggers. And in particular, you can have a situation in which you have some operator CK, which belongs to some complicated operator OX, where K does not belong to PS. And you can have some other operator O tilde, which contains the same operator CK, which contains the CK dagger at the same K, which does not belong to PS. So if you smooth these operators OX and OY and OY tilde, smoothing them just removes these individual CKs and CK daggers. But if you take the product, if you take something like OX times OY, or if you take a product of things like this, then this product will actually contain CK dagger CK, which is just NK, of course, and which does stay in the algebra after smoothing. So it matters whether you smooth first or multiply first. That may or may not, that determines whether these NKs at high momenta K are kept in as operators in your operator product. And so the commutator of these two operations of multiplication and smoothing is built out of precisely these operators NK at high momenta. As you see here, and the commutator of these two things is precisely what you call the singular coefficients of an operator product expansion. So basically what I'm saying is that these NKs here they're constants, they're structure constants of your continuum QFT. And they end up entering into your OP coefficients and all the other various things like central extensions of various current algebras and things like that. That's how these NKs enter, and that's what that's how you get all this extra structure that continuum QFTs have. And then, yeah, and you can see here if you smooth first and then multiply, then you will get absolutely no UV effects. There will be no connections between CKs and CK daggers in different operators, and then that's what you normally call normal ordering of operators. So everything that you call normal ordering is essentially behaving. You can recast it on the lattice as saying it's a multiplication of smoothed operators, as opposed to multiplication of operators before smoothing. And this is not just a formal statement. I can actually use this to calculate various super interesting quantities. Like in an earlier paper from 2019, I was able to use precisely this prescription to calculate the entire non-trivial operator product expansion for the Ising CFT, including the fact that there's some non-trivial statement that that if you have two operators sigma in the CFT, you have something that looks like this, plus an epsilon operator times x minus y or something like that, 2 3/4, and so on. So you can actually calculate the coefficients and in particular these powers explicitly from the lattice, again, without ever assuming anything about conformal symmetry. So, so it really gives you a good correspondence between these things. So that's all very nice. It's useful and powerful, and it gives you an idea of where these extra structures that continuum theories have arise when you think about lattices. Okay, are there any questions? I can go back to the actual slide with content. So if not, or if you need more time to ruminate on this, I will move forward to talk about the last thing I want to say, which is how induced Simons terms work, and that will also highlight some extra interesting stuff about how this entire story works in a path integral language and what's the extra stuff that you need to keep track of when thinking about path integrals. Okay, so everything I said so far was focused on spatial smoothing. So, so basically I was smoothing everything on a single time slice, and I was talking about how to get operators which smoothly vary from point to point on some lattice on just a spatial manifold. I didn't say anything about time, and this example is also going to tell you how time gets involved and like gets sort of put in on the same footing as space when you think about path integrals. And in addition, it will illustrate some things about Chern-Simons theories, which are, I think, super interesting. So to illustrate how time works, consider a super simple theory, like stupidly simple. It's a two-dimensional theory, just a quantum mechanics of a single massive fermion. So the Hilbert space is two-dimensional, and the Hamiltonian is this, and you absolutely have no excuse not being able to solve this theory. It's a 2x2 matrix you need to diagonalize. The only interesting operator in the theory is this fermion bilinear. You can call it a current if you will, kind of trivial. And its expectation value at a temperature, at the inverse temperature beta is given by this. Again, absolutely nothing difficult in evaluating this. And at 0 temperatures, the answer is simply this, meaning that the ground state depends on the sign of this parameter m, the mass, and depending on the sign, the expectation of the current is given by this. The expectation of the current is either 1 or 0. Basically, depending on whether the ground state is an occupied state or an unoccupied state. So this is everything so far is exact and trivial. Now, the non-trivial stuff comes when I ask to derive the same result using path integrals. Now, there is first a completely exact way of rewriting various correlation functions of fermions as path integrals, as Grassmannian path integrals, of course also called Berezin integrals. This is all very familiar, and while keeping all the details in place, I can write down this thermal expectation value of the current as this path integral here that you see. So basically what I did is I take the thermal circle, as you know, and divide it into many small, into many steps of size d tau. and I define a number n0 as beta over d tau, like the number of sites on this thermal circle that I will be working with. And up to terms that are of order m times d tau, this is an exact statement. So, and I can always take d tau to be sufficiently small when writing this. So this is an arbitrarily correct statement way to express this correlation function here. Very good. Now, the interesting question is as follows. How do you evaluate this path integral? And of course, it turns out that this path integral is a horror to evaluate. Of course, we have some bilinear of Grassmann numbers in the exponent, which means that the path integral is really some determinant, and it boils down to evaluating a determinant of something that looks like this: omega d tau minus 1. I'm being cavalier about signs and stuff, but yeah, roughly you're evaluating a product of these, where omegas are, of course, the Matsubara frequencies, which are 2 pi over beta times n or something like that. N plus 1/2 perhaps, but yeah, whatever. So things like this. So you have to evaluate all of these. And evaluating this product is impossible. It involves delicate phase cancellations and things. And indeed, if you can do it numerically, and you can actually, of course, verify that you get this answer. But it's for different signs of m. I of course did not put in m here, but I should have. But yeah, like you get things like this. And it's a mess to do. You definitely cannot do it analytically. So, but instead, to actually get something that's calculable, you have to do something else. You have to assume a further thing, that your Grassmann fields eta tau are actually smooth in time as well. Unlike the spatial story that I gave you in the previous 40 minutes, the temporal story has absolutely no justification. So back then I said, oh, I'm allowed to do this essentially because these nks were constants of motion. So doing this projection doesn't actually change the Hamiltonian, and et cetera, et cetera. So this was all like a very well physically motivated projection, the spatial smoothing that I talked about before. But in the temporal case, there's absolutely no justification for doing this. You literally just take your expansion of each field in Matsubara frequencies, and you violently project it to a smoothed version, where instead of going all the way to this cutoff n0, you now go to some much smaller cutoff ns. So ns is much smaller than n0, but it can still be much greater than 1. And once you have done this, then these guys, these eta taus, behave just like the smooth fields in the spatial case. They obey relations like eta tau plus d tau is approximately eta tau, up to terms that are of order d tau.
Question.
So, yes, please.
Why is this any worse than the spatial smoothing? Because supposedly you're working in Euclidean signature, no?
Yes.
So you're working with the latticized circle, and you're smoothing out on that, no?
Yeah. So that is true. But what I want to say is that the following. So doing this smoothing. So if you now replace all these etas with their smoothed versions, and here you only have also the smooth versions of eta, etc. Blah blah blah. If you do this, then you get another quantity which I call J, capital J. And my point is that this quantity is not the same as the original one, as the one you want. So doing this temporal smoothing is going to be as I said, is unjustified, and you can actually explicitly check that it's not giving you the same answer for the path integral. Essentially, that's because that's saying that the product of, when you write the product of these guys over all omega minus 1, I'm just saying that this is not even approximately equal to the product of omegas over 1 over omega. So you can just expand this omega, this e to the I omega into powers of omega. So this is not the same, because omega can have values of 1 over d tau, and these values are important to get the exact answer, to get this microscopic answer which I raised. So in that sense, it's worse. So in the spatial case, if you ask for low momentum, if you ask for correlations of low momentum operators, then the existence of the pre-continuum basis guarantees that that those things will not depend on the high momentum stuff. Here, there's no guarantee like that, and indeed, the high frequency stuff will enter into expectations of J or everything else, really. It's perhaps counterintuitive in some way, but it's certainly true. This is a simple example where you can explicitly check that. But not all is lost. There exists a miraculous connection between these two objects, capital J and microscopic lowercase j. And the connection, you can just compute it very explicitly, is actually this. I think of it as a miracle, really. Like, so of course there are extra terms which depend on the size of ns over n0 here, but there is a universal term, ns independent term that controls the difference between these two objects, and this is this factor of 1/2. And so the way you should think about this factor of 1/2, it says that oh, you have chosen to work with smooth fields instead of the actual microscopic fields. That is not fine, but if you're allowed to manually take into account the various factors of 1/2 like this, then it's fine again. Then it's then you can keep working, and that is the smoothing perspective on why you need to introduce a Chern-Simons term, a one-dimensional Chern-Simons term, into the generating function of your theory. Because if you want to express this object J, this microscopic thing, as a derivative of some generating functional of some function z of a, then in order to account for this guy, and this is in the temporally smooth version. So if you just work with smooth fields blindly, you would just get this number here, which would not have any, which would miss this factor of 1/2. So then you add to this ZA, you add to the action in this ZA an explicit term, this improperly quantized term that just contains that will just give you 1/2 after you differentiate with respect to a tau. So this is a completely new and unfamiliar way of viewing the origin, as viewing the origin of contact terms. But the thing that is remarkable about it is that it does not require anything incalculable or any like tricky handling of some regularization or something like that. It works with perfectly regularized objects throughout, and it tells you what is the point at which you need to start including contact terms. It's really this smoothing, the temporal smoothing, which forces you to start including contact terms. So
question.
Yeah.
Does this fix the coefficient of this term?
Yes. So you can explicitly calculate, as I said, that for any m, such that m beta is much less than ns, this contact term is always this. and therefore, you manually need to add this contact, this transaminase term, and it's fixed. And you can think of it as sort of adding, this term. So you can think of this expectation of J giving you just 1/2 signum of M. If you compute it, minus 1/2. And then you can think of this extra contact term as giving you this extra 1/2. So the calculation, the comparison between the two expectations, the microscopic J and the smoother J, tells you that you have a fixed contact term 1/2 to add.
So I ask because this one-dimensional Chern-Simons, I don't know if my student is here in the room anymore, but with Ruslan and some colleagues in Swansea, Prem Kumar and people, we're also studying these one-dimensional Chern-Simons theories.
Oh, okay.
But this particular, the abelian one-dimensional Chern-Simons theories is kind of a nice, famous / trivial example, with the same motivation that you've said, which is that you have no excuse not to solve it. To illustrate what happens with the temperature dependence, with the apparent temperature dependence of the Chern-Simons coupling. Right, and so here you can kind of famously resolve it because in one dimension you can resum the whole Feynman diagram series, and show that you end up with a quantized Chern-Simons coupling, but only if you count all the diagrams. Do you see that kind of structure here, or does this automatically take care of that for you?
Okay, so I believe it automatically takes care of it. It takes care of this because I can compute both of these things. I mean, I don't use Feynman diagrams, so I do not see the exact structure that you talk about, but like I certainly can compute both the smoothed path integral and the microscopic one at any beta, and for any beta, even when it's not. So this relation that I said works at any beta actually. So at any beta such that, as I said, n times beta does not exceed the cutoffs. So including large values of beta, and the correct connection works. So I would say that the structure that this has to take into account everything. Now the question is, can you rephrase this? Can you rephrase the calculation I did in terms of path integrals, and then it might turn out to be the same as the calculation you had in mind.
Right.
Yeah,
okay.
Like I just never even, essentially I was just evaluating determinants, which of course I can recast as path integrals. I just never did. Sorry, as Feynman diagrams, I just never did. I just immediately solved the determinant.
Right.
Yeah.
Okay. Cool. If it can account for the, if the result is a quantized Chern-Simons level number in front of the integral A term, then that's great, because that means that the smoothing formalism is really counting, is really resumming the entire Feynman diagram series, which tells me that if I go to 2+1 dimensions, where this is in 0+1 dimensions, this is a great toy model, and I can certainly do this and then say, well, by analogy, if I go to 2+1 dimensions, then it's bound to work there. I'll just port the lesson that I learned in 0+1 dimensions to 2+1. But if your smoothing formalism is automatically counting for this, then maybe it'll automatically count for it in 2+1 as well.
It does. I mean, in the paper I actually did it for 2+1 as well, except that there are some extra subtleties, because So there the object you're looking at is no longer a 1-point function, of course, but you're looking at 2-point functions of fermions. So you're looking at objects that look like this, let's say, and you want to specifically say that this correlation function has some term that looks like k times signum of m times and let me call it k lambda, and then a nu lambda, or so, and then there's an I, or something like that. So I actually indeed see this in 2 + 1 dimensions. So so there you have also spatial smoothing. So now you have to worry about, you have to when you calculate these things, you have to worry about spatial smoothing and temporal smoothing, and in particular, you have to worry about normalizations of these things. So yeah, let me just say that there is some ambiguity which I don't know how to fix in terms of just obtaining the right normalization. So if you go from this, so you have the completely microscopic current, which I can call this. Then you go to a spatially smoothed current that I will call like this. So this is just spatial smoothing. And then you can also do the temporal smoothing. That will give you something that, I may call J mu of K tau or something like that. And so, so you have this interplay of these three objects. And what I want to say is that spatial smoothing may say that your correlation functions will have some overall prefactor, which will depend on this object Ks over n or something like that to some power. So or in other ways to say it is that these guys are dimensionful and might need to be rescaled by some factor like this. There might be a field strength or normalization of these currents. So
what kind of churn size term do you pick up in 2 + 1 dimensions?
So you will pick up this. So basically what happens is that if you naively, so the statement is this, if you will. So the statement is this: if you compare two currents like this, so they're temporally smoothed, then the imaginary part of this guy will be 0 if you just naively compute. And so that means that you need to manually add. Oh yeah, sorry. So if you just do the smoothed currents, you will get this. Whereas if you do if you look at the imaginary part of the microscopic currents, which I will denote like this, then you will see that this imaginary part does have, this structure. Yeah, mu lambda, whatever. And so that means that you need to add a contact term, which is precisely of the form some number times I times k lambda times e to the mu epsilon mu lambda, a nu or something like that, in order to say that in order to get this coefficient here, in order to get this term by differentiating the generating functional built out of just these smooth fields. That's the statement. And the non-trivial statement about this guy is that it doesn't just depend, there is some factor of 1/2, but there is also a non-trivial field strength normalization here. That comes from this connection between J microscopic and J microscopic non-smooth and J microscopic smooth. So there is some connection between these two, which up to an overall normalization, which needs to be fixed by looking at 2-point functions, which I haven't done yet. So basically I'm saying that I can see that I will need a contact term, but I have not derived yet that the coefficient will be precisely 1/2, which is what I see in 0 + 1 dimensions. That requires more work, but that requires a lot more work. But the work is doable. I just haven't done it yet because I have a finite amount of time.
You should smooth it up.
Yeah.
What about,
I hope this is clear, but yes, it's a lot of work, and you kind of have to get into the groove of it.
I can see how it arises. What about non-abelian terms?
I have not studied them at all. I'm starting to study it now.
I see.
There is no obvious obstacle to that. It's just that, you know, it's a new kettle of fish, which I just haven't, you know, approached. So I'm currently studying quantum mechanics.
I would imagine the finite time would be an obstacle to that.
Yeah, of course, yes. So yes, exactly. So I'm doing my I'm currently studying a single quantum particle moving on a non-abelian background. So that's kind of like the first non-abelian thing to study. And then, of course, the next thing to study is in 1+1 dimension to have multiple flavors of fermions, and then to see how, you know, the WZW model arises out of them by bosonizing. And then out of that, you know, once I understand that, then I can say, okay, now let me look at multiple flavors of fermions in 2+1 dimensions and see how a non-abelian transimultaneous contact term will arise. So the progression is clear, but it takes some time, because right now I'm essentially recasting all of differential geometry first in this planetary framework. So it's super interesting. It just kind of takes me a while to build up the structure. And it does not help that I have, like, you know, 1 year left of my postdoc, and, you know, I need to figure out how to actually use it. So yes. But yeah, like, there's a lot of stuff to be said here. So,
well, yeah. Reinventing quantum field theory and differential geometry seems like a good way to use your time.
Well, yeah, but there's like there's so much, like, you know, the question is which parts of it do I want to reinvent first? So, yes.
Cool, thanks.
But yeah, this is but I think at least the blueprint is clear. Like, you know, maybe I'm too optimistic, but I think that all of these things are all doable at this point. So yeah, so that's like the one reason why I'm happy, why I think that this is promising is that I was able to fix these coefficients correctly in 1+1 dimensions, where the analog of this calculation is actually the calculation of this commutator of currents, J mu and J nu, which at k and minus k, which is supposed to give you precisely something like a central extension of the Kac-Moody algebra. So you get something, you get that there is a universal, you know, number 1, I guess, or something, times k here. So in 1+1d, so that I was able to get. So yeah, I'm pretty sure that, you know, the 2+1 dimensional version I will also get. So it's just a question of nailing down all the normalizations right, which is straightforward but tedious. And yeah, I guess with that I should say that, you know, that does exhaust what I wanted to say for this talk. So it's good if you're asking questions and keep asking, but I actually do not have anything left on the agenda other than to tell you to read the papers. But yes, I can go back to
could I just see if you could even outline your derivation of the IR dualities?
Well, okay, so I can try to outline them, but it's really missing about a few important points. So well, let me tell you what the steps are, but I definitely will not try to derive it in any detail. But the idea is as follows. So first of all, we do know that there are lattice dualities, right? So there is Kramers-Vanier and Djordje-Wigner dualities on the lattice. And then when we talk about IR dualities in particular, let me take, for example, T duality. So here, this is some duality between this is a duality between let's say compact boson CFTs, or just call, like, let's call them compact boson continuum QFTs. And so what happens here is that you first need to define the bosonic continuum field theories. That's the stuff that actually takes some extra work, because the way bosonic theories work, so bosonic CQFTs, it's the algebra A, which has a pre-continuum basis, is not the naive one. So you can't just take some ZK model or something like that, something complicated like that, and just Fourier transform it like you can for fermions. The algebra, this algebra contains only tame operators, and that's a technical term for operators that never take you out of a particular subspace of small fluctuations. So what I mean by this is that so you start with some lattice theory, which is, let's say, a ZK clock model. So you have k sites at each spatial point x. You have k sites, and then first you need to go to an algebra A, which only controls small fluctuations in this target space around some background, around some point on the clock, and then so first you go to this tame algebra, and then you can smooth this algebra further and get a continuum theory. And so the non-trivial thing about deriving let's say T-duality is the following. So a standard lattice duality, standard KW, as you know, just maps these ZK operators to ZK operators in some way, and it involves these singlet projections. So it's a statement that a clock model will map to a clock model projected to a singlet over the overall ZK symmetry. Now the problem is that the singlet of the overall ZK symmetry is actually not a tame state. So it does not involve just small fluctuations, but you actually have to. It actually involves all possible windings around the clock. So first you need to modify you need to like find some alternative duality which really maps ZK gauged in some particular way. You take some subgroup of ZK and gauge it, and then that maps to some other ZK at some ZK prime or something like that, such that so first you need to find complicated lattice duality which does this. So this is related to the stuff that I was talking about when I actually last visited Cape Town, that you can actually do these things with Kramers-Vanier dualities, that you can sort of gauge parts of the subgroups and still have dualities. So so first you need to take a slightly more complicated version of Kramers-Vanier, which only maps which will only map subsets of the target space, and then from there you can you can say that under that duality, the tame operators will map in a certain way to other tame operators. And then you can ask, okay, so now you can say how the smooth and tame operators will map to each other. So, and then smooth, this duality KW star, not just K. So there is so this is in my I guess second paper. It's a relatively formal 10-page derivation, but in the end you actually get explicitly a statement about things like where does what precise operators map. So you don't just say something like phi goes to, or sorry, d phi goes to you don't get a statement that phi just simply maps to something like pi v in the dual picture. You actually get something like you also know what's the possible extent of this phi, like how large the fluctuation of this phi can be, and how large the fluctuation of this pi can be, and how these fluctuations map to each other, and things like that. So you get these like extra data, but yeah, I just have to apologize because there's absolutely no way I can reproduce the actual details like in real time now.
No,
yes, but that's the story. Basically, you need to find a twisted version of Kramers-Vanier which respects which works for small fluctuations. Basically, you sort of gauge what I mean is you sort of think of Kramers-Venia for gauged versions of this, where you sort of gauge motions by large intervals on this on this circle, so that the only non-gauged thing is this motion in a small interval here. And then you can write down the lattice Kramers-Venia for that, and then from that you can derive what we normally call T-duality. And it turns out that T-duality that you derive also comes immediately from the get-go with the standard duality between winding and momentum modes that you of course know from T-duality and so on. So everything works out beautifully, just that it takes a lot of, it's a very annoying thing to calculate in detail, but you can. And I think it's useful to know that you can.
Great. No, fantastic. Thank you very much. That was an excellent talk, as we've come to expect from your talks. I noticed that a bunch of my students have left the room, but that's okay. This really was a talk for me.
Well, yeah, I mean, like I'm glad. I mean, I don't feel offended because, like, of course, this is like, first of all, I'm like half an hour overtime, and then second, and then second, it's